All right, here. So number one, describe the current weather conditions at the following locations. In other words, what would it be like if you were there on the ground at location A? What would you experience outside? Brandon, what do you think? Not necessarily cold, and we'll talk more about the temperature. Just define lousy weather. Cloudy, precipitation, windy. All right, we've got a cold front passing through, so we're going to have cool air, and we'll get back to this conversation here in a minute. We've got cool air pushing into warm air. That's how I know it's a cold front, right? And it's got the triangles to let me know it's a cold front, and it's blue to let me know it's a cold front, correct? Cold fronts, we're going to bring clouds, precipitation. Sometimes there can be pretty violent storms at cold fronts. All right, how about location B? Location B. Roslyn, what do you think? Did you get that one? Did you skip it? Skipped it, that's all right. Haley? Fair weather. Clear skies. H stands for high pressure, right? High pressure air, because it's more dense, there's no room for water vapor. You're not going to have many clouds. You're not going to have precipitation. It's probably going to be nice and sunny, clear outside. Now, let's have this conversation now. Haley said cool weather. That's true, but we don't know how cool. This map, these surface maps, don't give us any indication of actual temperatures. It only gives us relative temperatures. What I mean by that? Yeah, this high pressure area, the air is cooler than the air surrounding it. It doesn't mean it's necessarily cold, though. This air could be 90 degrees for all we know. That would just mean that the surrounding air would be warmer than that. Right? Does that make sense? Likewise, in the wintertime, hello. Yeah, I can update the calendar. Yep, bye. If this was a map of the wintertime temperatures, this air could be like -10. Again, assuming the air surrounding it was warmer than that. So yes, the blue indicates that it's cool, but I don't know how cool based on just this map alone. I would have to have some other information in order to know that. The same thing goes for this red L. It's red because the air is generally warmer, right? But again, I don't know how warm. Could be 90, could be 20, I don't know, simply because I don't have that information on this map. All right? Question number 2, what type of weather front is currently passing through location C? Rosalind, I know you got this one.
It's an occluded front, and it's created when a warm air mass gets cut off by 2 cold air masses.
Perfect. So it is an occluded front, and we've got 2 cold air masses that are kind of squeezing together a warm air mass. And again, I'll get back to this a little bit more specifically in a second. I'll show you how all that works together. Okay? How about number 3? What does the red L represent? And describe what kind of things happen because of it. Jacob, what do you got?
Oh, I got low air pressure.
Okay, low air pressure. What's it called? Remember that C word?
Cyclone.
Called a cyclone. Okay, what kind of weather would we expect in this area? Go ahead, Jacob.
Lots of clouds, rain, bad weather that is happening today.
L for lousy is how I remember it. Lousy weather, cloudy, rainy, windy, much like we're having outside today. I'll show you our real map here in a minute of our actual forecast for right now. Tyler, just focus on what we're doing, okay? Yep, it's coming through right now. That's why we're getting all the rain. Okay? I'm going to come back to number 4 in a minute. Here's what I want you to do. Drop everything, push everything to the side, and just look at the board. This is a very important conversation we're going to have. Chapter 3 takes all of Chapter 1 and 2's concepts and kind of puts them together. So all the stuff we've been learning about so far, this is what it's for right here. Okay? Air always moves from areas of high to low pressure. So on this map, we should see air moving from this high pressure to this low pressure. From this high pressure to this low pressure. That's kind of on the outside of the map there. From this high pressure to, there'd be low pressure down here somewhere. From high to low, from high to low, from high to low, from high to low, high to low, high to low way up there. High to low, high to low, high to low. Does this make sense? There's high pressure up here to low. High to low. High to low off the map. High to low off the map. Right? What's the problem with the arrows I just drew? Bradley, what's wrong with them? Why? Okay. Well, what's wrong with them? Gwen? Boom. This is the northern hemisphere. We'll talk more about that in a minute. This is the northern hemisphere. So in the northern hemisphere, instead of drawing these arrows straight, I should give them a curve to their right. All right, so I'm going to do that. Instead of coming from here, this air is going to be going like that. And instead of going here, it's going to go like that. It sure is. Relative to Earth's surface, it is, yes. And since we're on Earth's surface, it's curving in our point of view. So we'll do this. I know, right?
Science. You amaze me. Science. What's science? You're missing your R. Tom.
And there'd be high pressure over here, and we'll draw it like that. And there'd be some high pressure up here, and we'll draw it in like that. And some high pressure up here, and we'll draw it in like that. And high pressure here, and high pressure here. And one more. I think I got them. Wow. Hi. Say that again? Exactly. Did you hear what Gracie said? She said it's like a drain. The high pressure drains into the low pressure. She's absolutely right. The air is moving from these areas of high pressure away toward the areas of low pressure, and then it kind of circles the drain, exactly what she was saying. Okay? No, it's approximately equal, just different areas. It's just the way this map is drawn. If we've zoomed out, you wouldn't notice that as much.
So, like, you could have two high pressure and one low pressure, and they're both going.
Yeah, they go everywhere. They all just interact with one another. High always moves to low. Yeah.
How come the middle of the cyclone not windy?
It's not as windy because the air doesn't really reach it. Do you remember watching that hurricane video? And they talked about the eye, and it's actually very calm. Because by the time that stuff swirls around in the hurricane, it rises before it gets to the center. Same thing is happening here. And don't forget this, we'll get here in a second. Air at these centers of low pressure is rising off the surface. Air at the centers of high pressure are sinking. Then it flows, rises, sinks. Flows, rises, sinks. I'll come back to that in a second. Okay, Leon. How does what? It moves counterclockwise around the low pressure, but clockwise around the high pressure. So you see it, the general pattern of air is this way here, but when it feeds into the low pressure, it goes this way. So they kind of make figure eights. The air is going to flow out, rise up, sink down, flow out, rise up, sink down. Why does the what? That's where we're going right now. All right, so here's the deal. Why this is so important. All of these air masses are being pulled into one central location around the center of low pressure, right? So where we are here in the northern hemisphere, we've got warm air being pulled in from the south. So this is pretty warm air coming here. Again, warm air being pulled in from the south. We've got cold air pulled in from the north. Whoops, I should probably write the right word. We're going to call it cool. And we've got cool air being pulled in from this direction. Where these different temperature air masses meet are those weather fronts. So if I look at cool air, follow the arrows. Cool air is being pulled this way into warm air. And when cold air pushes into warm air, we get a cold front. When cold air pushes into warm air, we get a cold front. When this warm air pushes into cold air, we get a warm front. Does this make sense? And where this cold air and this cold air were next to each other, and this warm air was sneaking up in between them, it eventually got cut off, and there's your occluded front. Oh. Okay. So essentially you get 4 quadrants of air here. You get cold air and cold air from the north, east, and west. You get warm air from the southeast and southwest. And those things all get pulled to the center location, and they start to meet around that low pressure center, and they form the different types of weather fronts. That's the whole point of this. And as this air meets in the middle, it starts to go up, it gets forced to rise, right? Heated air rises, cools, the water vapor contracts, it forms clouds, precipitation, all in this area. As that air is cool now, it sinks back down at those high pressure areas. And as it flows across Earth's surface as wind, it's going to start evaporating that water vapor, reaches the center again, cools, condenses, precipitation, air sinks back down. It just repeats this process over and over again. So if you think about this three-dimensionally, we've got air here at the surface, flowing along the surface, that's the wind we feel, rises into the atmosphere, sinks back down, flows across, rises up, sinks back down, flows across, rises up, sinks back down, flows across, rises up, sinks back down, over and over again. So basically we just have a bunch of convection currents. Oh. Remember those global convection currents? Trade winds, prevailing westerlies, polar easterlies? Those massive, large-scale convection currents? In this region, we've got prevailing westerlies pushing everything this way. But within that big band, we've got all of these. This is a convection current right here. High to low, rise, sink. High to low, rise, sink. High to low, rise, sink. So we've got all these kind of interconnected convection currents that are starting to move water vapor and air, circulate it all about, creating our weather patterns.
Why wouldn't it be a stationary front if they're both coming in, if they're both like...
Because they're slamming into each other. Now sometimes, like right along this line, stationary front just means the 2 air masses have met, but neither of them is pushing the other one. So there's not enough momentum behind the air to force the other one out of the way.
How do you know, how is there like enough pressure to push it into the other one sometimes, but not the other?
It has to do partially with the difference in the pressure. So the greater the difference in the pressure, the faster that air is going to move. The bigger the difference in air pressure, the faster the air moves. Correct. To make any front, you need warm air and cool air. What says that? Right. So what we've got, and that's the situation I was describing here. We've got a cold air mass here, we've got a cold air mass here, and we've got a warm air mass coming in from here. So as this warm air tries to feed its way up in there, these 2 cold air masses close in on it and cut it off. And they start squeezing that warm air out, and that's where you get your occluded front. But down here, there's no cold air mass forcing its way into this yet. So eventually what you'll see is this cold front starts to move further down here. This warm front gets shorter, and the occluded front gets longer, because it starts to squeeze that warm air more and more and more. See the warm air? There's a wedge of warm air right there. The blue is a cold front, which means I've got cold air pushing into warm air. Right, so this thing that I'm shading here, that's warm air. And as this cold air and this cold air start to squeeze that together, more and more of that air gets cut off. So this would no longer be warm air, this would be cold air. So this occluded front gets longer and the warm front gets shorter. And we can talk about more of that tomorrow.
She's
Okay.
with you. Maybe we should just like have.
It's all right, it takes some time to understand this. There's a lot of interconnected stuff going on.
Why does that happen?
All right, now, back to our other question here that we didn't answer. Number 4.
That's camera control.
Does this map represent northern or southern hemisphere? And how can you tell based on the fronts? Obviously, it's the northern hemisphere because it's a map of Europe, right? But how do I know that it's northern hemisphere based on the weather patterns? Where should I look? Where should we look to figure that out? Because remember, air in the northern hemisphere always turns to its right, and it's going to lead to these certain patterns. That's how the cyclones move. In the northern hemisphere, they move counterclockwise. Counterclockwise. Right, so the air goes to the right. Air goes to the right. Air goes to the right. Look at the way the arrows are moving around the center of low pressure.
Wait, what?
Look at the way the arrows are moving. Follow the arrows.
Okay.
Okay? Now, I don't have those arrows on this map, but I do have weather fronts. So if I follow my weather fronts, find a low pressure center, look for cold fronts and warm fronts, see which direction they're moving around the center of low pressure, follow those arrows. Boink, boink, meow, this way. See how the direction of the arrows is going this direction?
It's not kind of like every map, but like in the center right there on the low pressure, it's like the occluded front, it's like curving.
Yeah, it doesn't get that extreme most times. Not every map, no. And we're going to ignore the occluded fronts in this because they can do that weird thing where it looks backwards. Always look at cold fronts, always look at warm fronts. Same thing here. Cold front, warm front.
Oh.
Guys, you can stop. Look at the direction they're moving around this center. Boom, boom. If you follow it, it'll keep going counterclockwise.
She doesn't know.
Okay? So cyclones in the northern hemisphere move counterclockwise. Cyclones are those big red L's. Yes, ma'am. Because it's representing what it's doing. It's saying, hey, we got warm air pushing this way and cold air pushing this way, but neither of them are pushing the other one out of the way. So remember, they always show you which direction the air mass is moving. But since they're not going anywhere, they're just kind of stuck pushing each other. The H is an anticyclone, which would go, instead of counterclockwise in the northern hemisphere, it would go clockwise because air blows out to the right, out to the right, out to the right. And look which way that air is circulating around there. Clockwise. But when it goes into the center of low pressure, it goes the opposite direction. Brandon.
So what if you have a cyclone or right on the equator?
You don't. They don't really form there. If they do, they move away from the equator because the trade winds take them that way. They won't cross over the equator because there's that, remember the doldrums, that kind of dead zone we talk about at the equator? Air just doesn't cross the equator. So when you have hurricanes that form, they always move away from the equator, not towards it.
Why? Hey, say you're on a mountain.
Okay?
It's more low air pressure
Mm-hmm.
than at the bottom.
Correct.
But on a mountain, it's colder.
Correct.
Why is the low air pressure warmer when it gets cold?
As the air is heated, it rises, When you get far enough away from the heat source, which is the ground, it spreads out and cools down. So down here at sea level, the air is being heated by the ground, right? Ground absorbs energy from the sun. Ground gets hot, heats up the air above it like a pot of water almost. The air down here is nice and warm. It starts to rise, and as it rises, it gets further from the heat source, cools down, and starts to spread out. Becomes less dense, and it's cold because of that. What's that? Again, the high and low pressure you see on this map, it's not relative about height. It's relative at sea level to how hot or cold the air is at that location. Warmer air is less dense and starts to rise. Cooler air is more dense and starts to sink. Yeah, this has nothing to do with elevation. This all has to do with the heating and cooling of the Earth's surface. Okay? Let's look at today's map real quick.
Yay!
So let me update this. This was a few hours ago. There it is right now. This past weekend, we had a pretty nice day Saturday. It was pretty nice and sunny, nice and clear. Sunday morning was pretty clear. Throughout Sunday afternoon, we started getting some clouds, started getting some showers. Last night it rained a lot. This morning it's raining. This afternoon it's still raining. We had, originally this morning, this was all a cold front. This was one big cold front. So this past weekend, we were in this area of high pressure. High pressure air has clear sky conditions, right? So this past weekend was actually pretty nice because we were in this little zone of high pressure. As this cold front sweeps in, it's going to bring us the rain, the clouds that we had the past 12 hours or so. But look what's behind it again. More high pressure. So this is eventually going to push this out of the way, and we should end up with some clear skies the next couple of days because of this high pressure zone behind it. Now, throughout the day here, what we've noticed on this map as we update it, like I said, this used to be a cold front. Well, now look what it is. It's a stationary front, which means this warm air is pushing back harder than it was this morning, and it's kind of stalled it out. So we got cold air pushing this way, warm air pushing this way, but they're not moving each other. They're just kind of stuck. So we might see like some scattered showers throughout the rest of the day here until this high pressure zone pushes that stuff out of the way. Here, this is probably a small warm front because so here's a center of low pressure, which means air is moving around it like this. So this warm air is kind of pushing. And then up in here, we've got warm air that's kind of pushing up, cold air that's kind of pushing. There's a big cyclone up here. You can't see it, but there's cold air being brought down like that. So they're just kind of stuck right now over Ohio. We should see this start to move here in the next few hours, though. It's supposed to clear out by tomorrow, I believe. I really like these maps, mostly because the isobars are a lot easier to read on here than the other map, and they've got them clearly labeled for you. So remember, isobars show us the same air pressure. So for example, this line, if I follow it all the way across, goes off the map there. Everything that's connected to that line has an air pressure right here of 1,020. And as you move closer to the centers of high pressure, the very center of this high pressure zone is 1,027. That's pretty high pressure, which means the skies are going to be nice and clear here. Mm-hmm.
Like, those aren't, like, connected to anything? So, like,
Those are, so the 1019's got an underline under it. That is describing that L.
but they all do.
This one's describing that H.
So, like,
This is describing that H. If you follow the lines, they will be labeled somewhere. There's 1024.
so, like, even though they're not, like, directly on the line, like the 1020, they, like, still go to the higher level?
Right. So this is 1,020. This is 1,024. Inside of that line is 1,026.
So they still mean something.
They still mean something. Correct. Yep. And then as we go further towards low pressure, so we've got a high pressure center here, 1024, 1020. 10, 16. As we get close, there's a big low pressure center up here today. As we get closer to that, the numbers get lower and lower and lower. Okay? Questions? Yes. Does this make sense, people? And if not, hopefully we'll make sense in the next couple of days. We'll have another couple more maps like this where we'll kind of break them down and talk about high pressure, low pressure. The tough part to remember here, folks, is that this is a two-dimensional map, but the things they're showing you are three-dimensional. They are three-dimensional convection currents that are happening. Sinking at the H's, flowing to the L's, rising, sinking, flowing, rising, sinking, flowing, rising, sinking. All this air just keeps getting moved in these big convection currents. And then those convection currents get moved by the prevailing westerlies across the map. And this is happening everywhere around the world. It's all kind of cycling together.